Today we are doing problems in real numbers chapter. In this chapter we have first topic Euclid's division lemma, second topic the fundamental theorem of arithmetic, third topic irrational numbers, and the fourth one representation of real numbers in decimal form. So let us see the first topic, Euclid's division lemma. What is Euclid's division lemma? We will see the definition. Euclid's division lemma. For any two integers a and b, there exist other two integers q and r satisfying a is equal to bq plus r, where 0 less than or equal to r less than b is called Euclid's division lemma. Here a and b are two positive integers. We have other two integers q and r satisfying a is equal to bq plus r. It is Euclid's division lemma. Using this Euclid's division lemma, we find HCF of two or more positive integers. So let us see how to find the HCF of two positive integers using this EDL. Example: 255 and 867. Let us find the HCF of these two numbers using Euclid's division lemma. In these two numbers, 867 is a larger number, 255 is a smaller. So let us divide larger number by smaller number. 255 3s are 3 5s are 15, 3 5s are 15, 1 16, 3 2s are 6 1 7. Subtracting 7 minus 5 2, 6 minus 6 0, 8 minus 7 1. Dividing this 255 by this remainder 102. 102 2s are 204. So again subtracting 1 5, 51 remainder. Dividing this 102 by this 51. 51 2s are 102. Remainder 0. So 867 can be written as 255 into 3 plus 102. Writing each step in A is equal to BQ plus R form. Now 255 is equal to 102 into 2 plus 51. 102 is equal to 51 into 2 plus 0. This last step, A is equal to BQ plus R form. Here this B is called HCF of the given numbers. Therefore, HCF of 255 and 867 is 51. In this way, we will find HCF of two positive integers. Now let us see how to find HCF of three positive integers using this Euclid's division lemma. Example: 60, 72 and 108. taking first two numbers 60 and 72, finding their HCF using EDL. So I am dividing 72 by 60. 61 is 60, remainder is 12. Dividing 60 by this remainder 12. 12 5s are 60. So remainder is 0. Now writing in A is equal to BQ plus R form. 72 is equal to 60 into 1 plus 12. Second step, 60 is equal to 12 into 5 plus 0. Now this is in A is equal to BQ plus R form. Here this 12 is the HCF of 60 and 72. Therefore HCF of 60 and 72 is 12. This is the HCF of first two numbers. Now we will find HCF of the remaining number and the answer. That will become the final answer of this question. So 12 and 108. Dividing 108 by 12. 12 9s are 108. So remainder is 0. So 108 can be written as 12 into 9 plus 0. This is A is equal to BQ plus R form. Here HCF of 12 and 108 is 12. This is the HCF of 12 and 108 as well as HCF of given three numbers. Therefore HCF of 60, 72 and 108 is 12. In this way we can find HCF of three numbers. Now we will do this problem using Euclid's division lemma. Very important problem. Show that square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. Show that square of any positive integer is either of the form 3m or 3m plus 1. Solution. Euclid's division lemma is A is equal to BQ plus R where 0 less than or equal to R less than B. Here we will take B value as 3. Let B is equal to 3. If we write B value in this one, 0 less than or equal to R less than 3 implies R is equal to 0, 1, 2. These are the values of R. Now in step 1 we will take B is equal to 3 and R is equal to 0 and substituting A is equal to BQ plus R form. A is equal to 3Q plus 0. 3Q plus 0 is 3Q itself. This is A. We have to show square of positive integer. So we will do squaring on both sides. A square is equal to 3Q whole square. 3Q whole square is 9Q square. This can be written as 3 of 3Q square is equal to 3 of 3Q square I am taking as m, where m is equal to 3Q square. So we got this one, 3m form we got. Now in second step, I will take b is equal to 3 and r is equal to 1. Substituting in, a is equal to bq plus r form, 3q plus 1. This is positive integer. So square of positive integer, a square is equal to 3q plus 1 whole square. It is in a plus b whole square form. So a plus b whole square formula all of you know, that is a square plus 2ab plus b square. So according to that, this one will become 9q square plus 6q plus 1. A square plus 2ab plus b square. In first two, I am taking 3 common. 3 of 3q square plus 2q plus 1. 3 into 3q square is equal to 9q square. 3 into 2q is equal to 6 and 1. Now this is equal to 3m plus 1, where m is equal to 3q square plus 2q. I am assuming this 3q square plus 2q as m. This is the second step. Now one more step we have. B is equal to 3, R is equal to 2. Substituting in, A is equal to BQ plus R form. A is equal to 3Q plus 2. Now squaring on both sides. A square is equal to 3Q plus 2 whole square. It is also in A plus B whole square form. A plus B whole square is equal to A square plus 2AB plus B square. So I am writing directly 9q square plus 2 into 3 6, 6 into 2 12q plus 4. This I am writing as 9q square plus 12q plus 3 plus 1. This 4 I am writing as 3 plus 1. In first 3 I am taking 3 common. So that is equal to 3q square plus 4q plus 1 plus this one is as it is. That is equal to 3m plus 1, where m is equal to 3q square plus 4q plus 1. So in this way we can prove square of any positive integer of the form 3m or 3m plus 1 for some integer m. Show that cube of any positive integer is of the form 9m plus 1 or 9m plus 8 for some integer m. Very important problem. Let us solve it using Euclid's division lemma. Euclid's division lemma, that is A is equal to BQ plus R, where 0 less than or equal to R less than B. Let us take B value 3 here. Then 0 less than or equal to R less than 3 implies R is equal to 0, 1, 2. Now step 1, I am taking B is equal to 3 and R is equal to 0. Substituting in, A is equal to BQ plus R. A is equal to BQ plus R. But we have to prove cube of any positive integer is 9n plus 1 or 9n plus 8 form. So here this is a is a positive integer. So cube we want. So cubing on both sides. A cube is equal to 3q whole cube, which is equal to 27q cube. We have to bring it to 9m or 9n plus 1 or 9n plus 8 form. So for that I am taking 9 common. 9 3s are 27. So 3q cube. I am taking this 3q cube as m. So then it will become 9m, where m is equal to 3q cube. This is first step. Now second step. B is equal to 3, R is equal to 1. Let us substitute these values again in A is equal to BQ plus R form. A is equal to 3q plus 1. A cube is equal to 3q plus 1 whole cube. It is a plus b whole square form. So here I am writing a plus b whole cube formula. A plus b whole cube is equal to a cube plus b cube plus 3ab of a plus b. So using this formula I am expanding this. So it will become 3q whole cube plus 1q plus 3 into 3q into 1 of 3q plus 1. Now simplify. 27q cube plus 1 plus 3 into 3 9, 9 into 1 9, 9q of 3q plus 1. Again simplifying. 27q cube plus 1 plus 9 3s are 27, q into q square, 9 into 1 9 q. Writing in descending order of powers. 27q cube plus 27q square plus 9q plus 1. So 1, 2, 3 in first 3 terms I am taking 9 common. 9 of 3q cube plus 3q square plus q. Last one is as it is. So this is equal to 9m plus 1, where m is equal to 3q cube plus 3q square plus q. So this is second step. Third step. Taking b is equal to 3 and r is equal to 2. Writing these values in a is equal to bq plus r. 3q plus 2. A cube is equal to 3q plus 2 whole cube. Again this is in a plus b whole cube formula. So expanding. A cube means 3q whole cube. B cube, here b value is 2. So 2 cube. 3ab, 3 into 3q into 2 of a plus b. 3q plus 2. A cube plus b cube plus 3ab of a plus b. Now simplifying. 3q whole cube is 27 cube. 2 cube is 8. Multiplying these 3 times. 3 3s are 9. 9 2s are 18 cube. 18 cube of 3 cube plus 2. 27 cube plus 8 plus multiplying this 18 cube with 3 cube plus 2. 18 into 3, 54. Q into Q, Q square. 18 into 2, 36. Q into 1, Q. Now writing in descending order of powers. 27 Q plus 54 Q square plus 36 Q plus 8. In first 3 terms, taking 9 common. 9 of 3q plus 6q square plus 4q plus the last term is as it is. So this is equal to 9m plus 8, where m is equal to 3q plus 6q square plus 4q. So in this way we can show that cube of any positive integer is either of the form 9m plus 1 or 9m plus 8.